So hopefully this works. All right. So yesterday, if you were in class or on Zoom, then we're going to pick up where we left off. If you weren't, then just refer to Mr. Fullerton's videos. So we ended with discharging capacitors. We wrote a differential equation and solved it for the charge after we disconnect the battery and we reconnect it without the battery in the circuit. And so the capacitor starts with the total amount of charge Q naught. That's the charge stored in the capacitor after it was initially charged. And now it will discharge. It will start with an initial charge Q naught, and then that charge will decay according to this equation right here. All right. And so that's the charge, the function that describes the charge stored on a capacitor as a function of time t after we've thrown this switch right here. And just like we did when charging, we got an expression for the charge, the voltage across the capacitor, and the current traveling through the circuit. Now we're going to find the equivalent equations for the discharging of the capacitor. So if I want to calculate the voltage across the capacitor as it's discharging as a function of time, so I can write it as a function of time, that's just going to be the total charge on the capacitor as a function of time divided by the capacitance. Remember, capacitance is defined as charge over volts, charge over voltage. So just solving that for voltage gives us this. So I just divide this by equation for charge by capacitance. And so it's literally just Q over C times e to the negative t over RC. What's that? That's what I said. Now what do you think we call Q naught over C? What do you think we can call it?
Initial voltage.
The initial voltage across the capacitor, right? Yeah. So we can call that V naught. And so we can say that the voltage across the capacitor as a function of time will be equal to the initial voltage of the capacitor times e to the negative t over RC. Discharging capacitors is a little easy because they all behave the same. They all start at a maximum and then they all decay. Because when we do the current, well, the current's the derivative of charge. The derivative of this. That's kind of the interesting thing about exponentials. The derivatives. The derivative of e to the x is the only function whose derivative is the same thing. Now remember, though, that dq dt, or the current dq dt, the rate at which charge flows through the capacitor, flows onto the capacitor, is negative if it's flowing off the capacitor. Right? We talked about that. So I need to find my current as a function of time. And that's going to be the negative derivative of the charge with respect to time. Negative because the charge on the capacitor is decreasing. You can also, I kind of think of it as, well, the current loaded on in one direction, loaded the charge in one direction, so when it flows off, it's got to be in the other direction. It's two different ways of looking at it. And as you'll see, it's the only way that it'll make sense, because when we do the derivative of this function here, the negative's got to cancel. And so, current, as if, sorry, my brain is not working today. See, I can't even talk. It's not working very well today. So no questions. No hard questions, Gianni. Okay, so the negative derivative of that function there, so the negative derivative with respect to time of Q naught e to the negative t over RC. Q naught's obviously a constant, so that can come out to the front, times the derivative with respect to time of e to the negative t over RC. Negative. It was there.
Really small.
Did you get any sleep last night?
I did. I don't understand.
Just by order?
I've been working out again. And I think that's sapping all of my energy. And what's the derivative of e to the negative t over rc?
Negative T over RC e to the negative T over RC.
Negative 1 over rc. Yeah. Right? The t's the variable. So it's negative 1 over rc. So the negatives are going to cancel. So I end up with q naught over rc times e to the negative t over rc. Now, as we already said, Q naught over C is the voltage, the initial voltage of the capacitor.
Let's go to the door. Oh, wait, no, mine. They were just like bending over.
Okay. Q naught over C is the initial voltage across the capacitor. So I can say, well, that's initial voltage across the capacitor over R times e to the negative t over RC. Wait a second. What's initial voltage divided by resistance?
Initial current.
Initial current. So that's going to be the initial current times e to the negative t over RC. So discharging is real easy to remember. The voltage across the capacitor at time t after the switch is thrown is the starting voltage times e to the negative t over RC.
E to the negative T over RC
For everything, yeah. It's not like that for charging. Remember, the voltage increases, the current decreases, but the voltage increases, the charge increases. And when it increases, it's something times, in the bubble, in the parentheses, 1 minus e to the negative t over RC. Notice that we're seeing negative t over RC quite a bit. Okay. And notice that we're seeing the product of RC quite a bit. And notice that when we see RC, it's always closely associated with time t. Okay? So RC is a special thingy. Special thingy, and it gets a name. And because it's... What?
I said uh-oh.
And because it's no, it's not. Uh-oh. Because it's closely associated with time t, the product of RC is defined as the time constant for the circuit. And it gets the symbol because we don't have tau standing for anything else in physics except torque. It gets the symbol tau.
Hopefully you're not dealing with torque when you're also dealing with circuits.
Yeah.
Hopefully.
Hopefully, but yeah, sometimes you are.
I googled it. Apparently, it's called the reflection coefficient of a circuit.
What's that?
I googled. Apparently, it's the reflection coefficient of a circuit. Is that something else?
Reflection coefficient?
Yeah.
I don't know.
It's how much of a wave is reflected by impedance discontinuity.
Oh yeah, that's beyond the scope of this class.
How far behind? How far?
Not that far.
Okay.
Where do you see torque in circuits? Remember the capacitor that came out of my pool pump that I was hoping was the problem this last time, but it's not. The pool pump is totally dead. It started smoking when I tried to power it the last time. That capacitor is used to create torque because the impeller, because a pool pump, all it does is spins. That's all it does. But it's attached to an impeller which has openings in it that are in the direction that it rotates, and so as it rotates real fast in the water flows through it, right?
Does that work on the static friction in the spark motor? Is that why?
Yeah, it has to overcome the friction. Yeah, just with the normal AC voltage that you have attached to it, it's not enough to kick it over to get it to start spinning, and so you got to get additional torque from the capacitor to get that going. So yeah, you do get torques from RC circuits, but whatever. At that point, if you know what you're doing, then it's not a big deal to delineate the two. So the thing is that this is pretty important because so this is called the time constant. After one time constant, the value of whatever you're dealing with is within 63% of the final value.
Why?
Because I said so. See, I was ready for this question yesterday, but we didn't get there. Okay, give me 1 second.
Yeah, like E to the power.
Yeah, because one time constant. After, so sorry. When I shouldn't have. Yeah, this is poor wording. When time t is equal to the time constant tau, what I should have said, which is again equal to RC, then the value is within 63% of the final value. And that's because when t is the same thing as RC, then I get initial current times e to the negative 1, which is just I naught divided by e, right? And e, when you divide anything by e, you're getting about 63% left over afterwards. It's just exponential decay, right? God, my brain is not working. I apologize. So just think that when the time that has passed is equal to the product of the resistance and capacitance, then this is just e to the negative 1 power. So this is like initial current divided by e. Okay. And if you divide anything by e, 1 divided by e is 0.3678 or 0.37. And so you get about 37% of the current is left over. And so you're within, yeah. Oh my gosh, my brain is hurting. The point I'm trying to make is this, and then the main point here, after 5 periods of time, then the value, because you notice that in these questions, in these situations, it's after a long time, or what I've said that several times the last couple of days, after a long time. When we say long time, we mean after 5 time constants. After 5 time constants, the value is within 1% of its final value. Okay. So you take the resistance. Notice that you can increase the time constant by just increasing the resistance in the circuit or increasing the capacitance of the circuit. So as the resistance of a circuit increases, the longer it's going to take to discharge or charge a capacitor. The bigger the capacitance, and I'll show you this graphically in a second, the bigger the capacitance, the longer it's going to take to discharge or charge a capacitor. Okay. That's why whenever I charge this thing, which is a capacitor, and then I discharge it with this thing, it sparks very quickly, right? Now, technically, when I do that and I touch it, there's still charge flowing through it, because if I do it again, then I get little sparks. So it takes a little bit of time, but it happens much more quickly than it does when I discharge this. And that's because there's very little, essentially no resistance in this guy here. So the resistance in that circuit is very, very small. So the time constant is very, very small. Even if I got a large capacitance, the resistance is very, very tiny. And so the discharge rate is gigantic, right? Does that make
capacitance is probably pretty small too.
I think this can hold quite a bit of charge, actually. But I'm not really sure, honestly. I knew that like a week ago, but I'm telling you, I can't remember anything right now. I don't know what's going on. I had a basic question last period in AP Physics 1, and it stumped me. And I was on video, too, like I am right now. So that's wonderful. Okay, so let me just show you that real quick. So I'm going to... Oh, no. You need some?
Yeah, I'm gonna watch first.
Okay. You really want to? This is my least favorite class, you know that, right? Okay, so I'm...
Are you using your white camera at home?
Yeah.
Okay.
Wait, at home?
For the kids at home?
Yeah. All right, so I'm gonna do this capacitor again, which we've already seen. I'm gonna charge it and discharge it and measure the voltage and the current. But then I'm going to take this capacitor, which it looks tinier, but it actually has much more capacitance. This is a 1 farad capacitor, so it can store a lot more charge than this one. This is about 100,000 microfarads, so you can do the math there. Hopefully. I can again because my brain isn't working today.
Can that be 100 farad?
100 microfarads.
Oh, that doesn't know. Okay.
Close. Close. All right. Sorry, Ms. Richmond, my brain is gone.
That's okay, because I'm having problems with my camera. Trying to see how you had it
All right.
I think he is too, because he didn't end up recording the audio.
Yeah. I've had some issues lately.
Well, I think he has. I don't think he's using the microphone for his camera.
Yeah, I think that's
I think that's
computer issues.
one microphone over there.
No, but the other day, it didn't record anything. Okay. So I'm going to charge this capacitor. I got the light bulb so we can watch the light bulb as the charging happens. And of course, what's going on? Oh, that'll do it. Come on, Trenton. Jeez. There we go. Notice it's not a nice exponential curve now, right? I'm using the light bulb right now. The light bulb is not ohmic, so I should probably be using a resistor. Let me actually replace that with a resistor. All right. And let me do the discharge. Since the capacitor we know is already charged, let's do the discharge. Why does it look like it's increasing? Uh-oh.
It's going the opposite direction.
Yeah, it's starting with negative voltage, and it's approaching 0. Start with maximum current, and it's approaching 0. Now it looks nice and smooth, right? Because now I'm going through a resistor that is ohmic. The light bulb is not ohmic, and so it's not going to obey Ohm's law, which is kind of inherent within the equations that we've been dealing with. The Ohm's law is definitely there. And so if I charge it again, it's fully discharged now. Let's do it again while charging. Oh, I have my current meter reversed. That's why. Okay, but this is what we expect, right? And what I'm showing you is that after 5 time constants, if I multiply the resistance and the capacitance of the circuit, after 5 of those time constants, I'm within 1% of the final value, which means when I say after a long time, after the switch has been closed, that's what I'm dealing with. Okay. Now let me replace this capacitor with the 1 farad capacitor. And let me do what I should have done before.
Isn't that capacitor now just sitting there charged?
Yeah,
I touch it.
that's,
It doesn't mean that there's not enough voltage to.
yeah, that's not dangerous.
They wouldn't allow anything dangerous in schools.
Oh no.
They allow schools and stuff.
I'm not gonna lie, a few years ago we found a little vial of mercury in one of the supply rooms. It's pretty interesting. Okay, so this is initially uncharged. Oh, I have it closed, dang it. So this is a much higher capacitance. And as you can see, it's gonna take a whole lot longer to charge it, right? Oh, I have these guys on backwards too. It's going from a negative voltage to a more negative voltage, just so you know. And so I have to set the settings here. This is going to keep going for a long time because that's 1 farad capacitor. So it's going to take a whole long time, real long time. That's the time constant is much larger than it is for the other guy. So a few times longer for sure.
It's 5 times the resistance.
What's that?
It's 5 times the resistance. Because
5 times the capacitance. I'm using the same resistor.
yeah, but like if the capacitance is 1 farad, then wouldn't it be 5 times the resistance?
Would what be 5 times resistance?
The tau. Like if you're doing 5 time constants, wouldn't that be the same as?
Well, if you keep the same resistance, then you would just have five times bigger time constant. If you had 5 times the capacitance. Remember, capacitance is kind of like resistance, but it's not.
Capacitance is 10 times.
100. Well, you tell me 100,000 microfarads versus 1 farad.
Right.
100,000 microfarads is 0.1 farads.
A tenth of farad,
Yeah, so it'd be tenth.
I think what he's trying to mean is basically tau would just equal the resistance. It's the capacitance is just straight up 1 farad.
Yeah. Oh, yeah.
Yeah, that's how.
Okay. Yeah. Sorry. I'm telling you, my brain ain't working today, guys. This is gonna be an awful video
yeah. If it even records.
if it even records.
This is the one video that will record.
Probably, yeah. Not yesterday, where I feel like I was on my A game. But anyway. Okay, so that's what I mean, and we're gonna solve some example problems now that'll give you some practice with this.
Is this the school?
Hmm?
Is this the school one?
Yeah. You happy about the switch?
Now, I can't get my camera. This won't recognize the camera.
Oh, that's weird.
Yeah, I mean, I'm having all kinds of issues.
I haven't had any problems with that. I have it plugged into this guy. Straight into that. It works just fine. Are you using it with your camera or with Zoom?
Well, I'm trying to record a lecture.
Yeah, I just record from the camera app. That thing. I have Zoom here, but then this is what I record with. But again, it hasn't been working, so I don't know if this is the best way of doing it.
Do you have like your own laptop that you can test it on? Have you tried that?
Yeah, it works on my laptop, but that's my laptop. I'm tired of spending money and using my stuff. I'm just being, just being a little facetious. Okay, I wanted to see, because I'm gonna have to get something. I'm gonna have to do a heat ticket, I guess.
Yeah, probably.
Sorry for the interruption.
No worries. I don't like these guys anyway. I'm just kidding. All right, in the laboratory, you connect a resistor and a capacitor with unknown values in series. We're starting with that one. With a battery of EMF epsilon equals 12 volts. You include a switch in the circuit. Just so you know, like the hardcore calculus that we did to generate this, it's not often that you have to do full derivations like that, as you'll see, especially in the second FRQ that we'll do here. You include a switch in the circuit. When the switch is closed at time t equals 0, the circuit is completed, and you measure the current through the resistor as a function of time as plotted below. And that's what we expect to see. The current as a function of time will be reduced as the capacitor is being charged. A data fitting program finds that the current decays according to the equation I of t equals initial battery EMF over the resistance of the circuit times e to the negative t over 4. Right? Using using common symbols for the battery, the resistor, the capacitor, and the switch, draw the circuit that you constructed, show the circuit before the switch is closed, and include whatever other devices you need to measure the current through the resistor to obtain the above plot. Oh my God. Label each component in your diagram. Okay, so we need a battery. Here's my battery. And you can do it like this, or you can do just a single battery cell. Either way is fine. The resistor. So it's got to go through a resistor. The capacitor. And the switch. But that's not it. Because it also says include whatever other device you need to measure the current through the resistor to obtain the above plot. Ammeters must be connected within circuits in series or parallel. Series. Remember, they have to feel the current flowing through them. So where can I put it in the circuit? Anywhere. You can put it anywhere, right? So I can put it right here. And an ammeter is just a circle with an A in it. Voltmeter is just a circle with a V in it. So there's my answer to part A. This is a FRQ from an AP Physics C exam, by the way. Both of these are. The second one we did was from 2019, so it's very recent.
Are we gonna have a
For mechanics, yes.
Not for this one?
Probably we're going to be very short on time. So, I mean, I can give you one, and you can work on it as like a study aid. Because not only next week, it's like 3.5 days, man. I forgot about that when I was doing my planning. I'm like, oh gosh, more time than I need.
Oh, isn't Thursday? next
Thursday's
week?
half day, Friday's off. Yeah.
Is Monday off?
No.
Oh, okay.
Okay. Having obtained the curve shown above, determine the value of the. That's it. That's the answer to part A. Right? We're good. That's full points right there. Number B. Having obtained the curve above, determine the value of the resistor that you placed in this circuit. So, how can I get the resistance there? Well, this is a single circuit with a resistor, voltage epsilon, capacitor C, switch S.
Can you solve for resistance there, I guess?
Yeah, we can solve for resistance by using, because what happens when you throw the switch? The capacitor acts like a, immediately after you throw the switch, the capacitor acts like a wire. And so initially, with the initial current, the only resistance in the circuit, the only voltage drop in the circuit is across this resistor, and so Ohm's law works. So I can say that epsilon, the battery voltage, equals the initial current through the circuit times the resistance of the circuit, which is just the resistance of the resistor. And can I get the initial current from the information given?
Yeah.
Yeah, what is it?
0.010.
0.01. So what do we have to find again? Resistance. So the resistance is going to be battery voltage divided by that initial current. Well, we know our battery voltage is 12 volts. We know the initial current is 0.01 amps. And that's going to be what? 1201 ohms.
Wait,
Just
1200, I think.
no one at the end.
12 divided by 0.5.
Oh, what am I?
So multiply by 100.
Oh, Timothy, make me look dumb. Wow. Wow. Oh, man.
Well, what happens if you put that on an AB exam? Is you're not going to point?
Oh, you probably get the point. If I was grading, I'd give you the point.
They just stare at it for a moment and then
They'd probably chuckle a little.
reluctantly check.
Okay, what capacitance did you insert? Meaning find C for the capacitor. What capacitance did you insert into the circuit above to get that result? How can we get the capacitance from this information?
R times C equals 4.
Yeah. Was that Joel? Or was that? Yeah. Nice. Yeah, we couldn't get that. This is easy. This is just Ohm's law. Though we need actually what we talked about today, or what you noticed in all of the equations that we've been dealing with the last couple of days. We know that the time constant is in the denominator of the exponent on E. And so we know that RC equals 4. So for part C, we just have to set RC equal to 4. The math on this problem is actually quite easy. It's just that you got to set it up properly. So RC equals 4. So C equals 4 over R, or 4 divided by 1200. So that's going to be what, 0.033 farads. I'm going to do that on my calculator though, because I don't trust myself right now. 0. Or I could say 3.33 millifarads. I could say that, right? Not too bad, right? Any questions, comments, concerns?
There's used to be. Oh, there is. I'm stupid.
What's up? Don't worry, man. You're not the only one. Okay, number D. Before we get to number D. You are now asked to reconnect the circuit with a new switch in such a way as to charge and discharge the capacitor. And we haven't really talked about this yet, so I'm going to show you. When the switch is in the circuit in position A, the capacitor is charging. And when the switch is in position B, the capacitor is discharging. So with a single switch, I want to be able to charge capacitor, discharge capacitor, charge capacitor, discharge capacitor. And when the switch is in position B, the capacitor is discharging as represented by the graph below of voltage C across the capacitor as a function of time. So what I've been doing up here with this guy is not the same. I've been connecting one switch with the other one disconnected. And then I disconnect that one and then connect the other one. But you might say, well, couldn't I configure that if I had a three-way switch that I could just move from here to here and reconnect the circuit that way? Yeah, sure. Really, I could do it with one of those switches. And then it gives you the graph. Obviously, that's what we expect. The voltage we expect to climb when it's charging, and then it exponentially decay when it's discharging. So we want to draw a schematic diagram of the RC circuit that we constructed that would produce the graph above. Clearly indicate switch positions A and B on your circuit diagram and include whatever other devices you need to measure the voltage across the capacitor to obtain